Now look at this idea of creating reduction formulas, sometimes called recurrence formulas, but it's really useful if you're trying to find the integral of something to some power, and that power's high, and you know that you're going to use the same strategy again and again and again and reduce it down. Well, let's just create a formula to save time. Often it's done by integration by parts. That doesn't mean 100% of the time, but a lot of the times it is. There's something like this. I've got the integral x log x to the power of 3. If I just say, well, that integral n, so whatever the power is that. All right, I'll do it by parts, and I want to reduce that power down so it makes sense that the log x to the power of n would be what I'm going to differentiate, because that will reduce the power. Plus also integrating log x to the power of n would be a bit tricky anyway. So the dv becomes x uv minus the integral of v du. But if you have a look at my integral here, the v du, the actual integral is of the same form, it's just that the power has changed. We can calculate the first bit out, substituting 1 we get e squared on 2. Okay, I've now got this formula. E squared on 2 minus n on 2 times I n minus 1. I reduce the power by 1. Well, I wanted to find I3. So I3 will be e squared on 2 minus 3 on 2 I2. But we can again use the formula for I2. And we get e squared on 2 minus I1. Now I can use the formula for I1, and I get to I0, but I0 is very nice because now we're saying that log is to the power of 0, and anything to the power of 0 is 1, and the log has now gone. I'm just going to find the integral of x dx, substitute in, and there's my answer. Oh, hang on, I can group those two together, can't I? Yeah. So we get e squared on 8 plus 3 on 8. So it brings it down to a much simpler integral. So I've reduced it down. Now, some people like to apply the formula in reverse and actually start at I0 and work out what I0 is, half e squared minus 1, and then go, all right, that means I1 will be e squared minus 2, and then build it up and get the same answer, obviously, for I3. Probably a rarer way of doing it, but some like it that way, some like to actually reduce it. Let's say integration by parts is the commonest, if that is a word. Is that a word? Commonest. Anyway, way of doing it, but it's not the only way, of course. Trig identities can come into play as well. So if I wanted to find the integral of cot to the power of n, and I want to find I6, I'm not going to use parts, because what I know about cot and tan, I use the same idea every single time regardless of the power. So I'm going to use that idea for cot to the power of n. And that was, I'll extract out of the cot n cos squared. And the cos squared I can change to cosec squared minus 1. And I can now split that into two integrals. The first integral is something I can do because I've got it as derivative times function. And the second one, I've reduced the power of the original integral. So if I did the substitution, u equals cot x, so to use minus cosec squared x, it becomes u to the n minus 2, or the negative of it. I can add 1 to the power over the power on that, and I've got a formula. Mind you, having u there doesn't really help me for my formula, so let's sub back in, and there we go. So I've got minus 1 on n minus 1 cot n minus 1. Find I6. Well, hang on, before I do that, keep an eye out for this. If it's the reduction formula ends up being something like in plus some constant times the other one, there might be plus some other one as well, then actually these formulas can be done a lot easier. It's usually when it's a show that, so you know where you're going to and you've got to show it and you spot that. So had that last question been hey, show that the formula's this, and I look at it and I go, hang on, look at this. The coefficient of the thing I'm reducing to is -1, which is just simply a multiple of the other one. How about I just work out what in plus in minus 2 is? That would become the integral of cot n plus cot n minus 2, which has a common factor of cot n minus 2. Cot squared plus 1, I know that's cosec squared. Oh look, I've got derivative times function, that's minus cot n minus 1. Now I just rearrange it and I've shown the formula. So just keep an eye out for that and show that once, if that happens to be. Alright. We had to find I6. Sub n6, I've reduced it down. Now it's I4, so this one's reducing by 2. Now I've got to find 2, so that's I0. That's where I stop, because cot to the power of 0, well, that's just going to be 1, and I get the answer there. Maybe it's a combination of parts and other things, algebraic manipulation. So this formula, and they've given us a hint in that we're going to be reducing it by 1. 1 plus x squared to the power of n. So u, 1 plus x squared to the power of n. Du, so I'm doing it by parts, is going to be 2nx 1 plus x squared n minus 1. Oh yep, okay, that's going to reduce it by 1. Dv becomes dx, v is x. So sub that in. Now look at the integral. It's not quite a multiple of what I originally started with, and that's where the algebraic manipulation is going to come into play. That x squared I could rewrite as 1 plus x squared minus 1, and then split that into two integrals. The first one, 1 plus x squared times 1 plus x squared to the n minus 1, and the second one's just 1 plus x squared to the n minus 1. In other words, I've now got two integrals. Both of them are in the form of the original integral. One's to the power of n, and the other one's to the power of n minus 1. There's my formula, but it's not quite right because I want to make in the subject. So I need to move the 2n in over to the left-hand side. So I'll do that. Now divide by the 2n plus 1, and we have a formula for in. Very old HSC question. 1987, my goodness. In is that particular integral. They're giving us a prove that. Unfortunately, if I was to rewrite it, it would be n times in and n minus 1, in minus 2. So I can't use that addition idea because I haven't simply got a multiple of the other one. All right, cos n. Now, cos integrals. We use different techniques depending on whether the power was odd or the power was even. So unlike that cot one that I did, I said, I'll just apply that idea. Here, well, which one of those two ideas would I apply? I don't know. Is n odd or is n even? So I'm not going to do either. I'm going to do it by parts. I'm going to split it up into two things though. Because notice I'm going to reduce it down n minus 2. Well, if I just differentiated n, it would get down to n minus 1. But if I split it into two things and make the u cos to the n minus 1, when I differentiate that, I'll get n minus 2. And then that means my dv is cos x, so v becomes sin x. Okay, let's plug that in. uv minus integral of v to u. But I've made it a plus because of the negative there. Okay. Again, looking at my integral, I don't have exactly the same, but now I can play around with the sine squared. I'll make the sine squared 1 minus cos squared, and my actual definite part, that's all going to be 0, isn't it? Because we've got cos of pi on 2, that's 0 in the first one, and sine of 0 in the second one. Bang, that's all 0, that's going to go away. I'm left with two integrals, and now both of them, yes, they're in the same form as in. Great. So I now know that's n minus 1 n minus 2 minus n minus 1 in. We want to make in the subject of all that. So playing around with it, we get the formula that they've asked us to show. So we have to find I5. I5 forfeits I3, but I3 would be 2/3 I1. But for this one, that's where I've got to stop because I'm reducing by 2. I can't go to I negative 1. That doesn't make sense. So we're just integrating cos to the power of 1. It's still a simple integral to do though. Integrate cos, we get sine. Substitute in, and we have our answer, 15ths. Alright, let's have a look at this HSC question. It was quite good. They've given us Jn is that particular integral. First part, I suppose first part is a nice gift mark. Just work out what J0 is. So if I sub in 0, well x to the power of 0 is 1, I'm just finding the integral of e to the minus x. Substitute. Okay, there it is. It's 1 minus 1 on e. Very generous mark when you think about it, but probably because this is going to be useful in a later part. So they say, we'll get that bit of information. Show that that Jn to that integral is always going to be less than or equal to 1 on n plus 1. So what do I know? Our integral is going between 0 and 1. And when I travel between 0 and 1, well, e to the minus x would have to be travelling between 1 on e and 1. I've basically applied the exponential function. That's okay. E to the minus x is continually decreasing. Therefore, the inequality signs flip around. E to the power of 0 goes to the right-hand side, which is 1. And e to the power of negative 1 goes to the left-hand side. Okay, I now know that's where e to the minus x is. Now our integral that we're trying to show is always less than that. Well, what I now know is that this integral must be less than or equal to this integral. Because the coefficient of e to the minus x is travelling between 1 on e and 1. So I'm always multiplying by a number that's less than or equal to 1. Therefore the area under this curve must be less than the area under this curve. Well, let's integrate then the x to the power of n, sub in, we have our result. It's the idea of using calculus to prove an inequation, the area under the curve. Now we actually have to find our reduction formula. And they're saying, well, this is what it'll end up being. Go and show that. And again, unfortunately, we don't have a nice multiple, so I can't use the addition trick. There's Jn. I want to reduce it down by 1, so we'll make x to the n the u. To u. There's the v. Substitute it in. Now, my definite integral part. Good, that's going to create the minus 1 on e. And now if I look at the integral itself, yes, it is the same, and I've reduced the power by 1. So we have our result. Use parts 1 and 3, and by mathematical induction, show this, that Jn actually can be written like this. N factorial minus n factorial on e, the sum of all the terms going from 0 to n of 1 on r factorial. Right, so that's what we're trying to show. Prove it's true for the first case. The first case in this case is actually 0, not 1. And that's why, I guess in the very first part, we found what J0 was, because we're going to show this is the same thing. So if I substitute in 0 factorial minus 0 factorial over e, well hang on, that's just 1 on e, because remember 0 factorial is 1. So I've got 1 minus 1 on e times the sum of 1. So yep, it works for 0. We will now assume it's true for k, and I'm going to prove it's true for k plus 1. So that is what I'm trying to prove. Okay, start with the reduction formula. That will allow me to put my assumption in. There's my assumption. I'm going to expand this out, but nicely. K plus 1 times k factorial must be k plus 1 factorial. So we've got the first bit. Now, minus, again, k plus 1 times k factorial is k plus 1 factorial. Ooh, that should be in parentheses there, because it looks like I'm saying k plus 1 factorial. The sum of, okay, how do I get there? I'm going to play around with this 1 on e, and I'm going to rewrite it as k plus 1 factorial on e times 1 on k plus 1 factorial. Because if you have a look, here, the coefficient of this sum, and remember I'm trying to get everything into that one sum, that's what I'm trying to prove. So I need the coefficient to be k plus 1 factorial on e. So I made it k plus 1 factorial on e, which changed it to, oh well, I've got to multiply by 1 on k plus 1 factorial. But have a look at the general term. It's 1 on r factorial. I've got 1 on k plus 1 factorial. It's the next term in this series. And that was what we're trying to prove. So hence it's true for k plus 1 if it's true for k. And so on and so on and so on. Oh, but it didn't stop there. Now use parts 2 and parts 4 to prove that e is equal to this limit as n approaches infinity of all that. What do I know about Jn? Remember part 2, we proved it was less than or equal to 1 on n plus 1. I've just added in the 0 as well because, well, it's got to be positive, we know that. Sub in what we just found, so I'm now using part 4. Somehow I've got to get e out of this. Well, I want to get e. I'm getting rid of this n factorial, so what have I done? I've multiplied both sides by e on n factorial. So the n factorial just became e. The coefficient of the sum disappeared. And then the right hand side now becomes e on n plus 1 factorial. So I'm going to try and trap it between 0 and 0. If I take the limit of all three things, well, obviously the limit of 0 as n approaches infinity is 0. It's not going to change. In the middle one, hang on, the limit of e as n approaches infinity is also going to stay as e. It's a constant number. So really, I could now say it's e minus the limit of this sum. Well, hang on. If I've now trapped it between 0 and 0, because remember, on the right-hand side, look at what we've got, as n approaches infinity. But we know if we've got infinity on the bottom of the fraction, then that's got to be approaching 0. So I've now sandwiched it, squeezed it, whatever you like to call it, but it's between 0 and 0. Well, that means that must be 0. And now I just move e to the other side, and I've proven the result. Fun, hey? Okay, so 4H, playing with our reduction formula.